Dear students, welcome to this NPTEL course on machine learning. I'm Carl Gustav Jansson, professor at KTH. I'm responsible for developing and running this course. This is the first lecture of the first week of this course, and the purpose of this lecture is to relate machine learning to some other important relevant areas, but also to give you an overview of the content of the course. The purpose of this course is to give a broad introduction to machine learning as being a subfield of artificial intelligence and computer science. The course is not aimed to be a professional course in the sense of giving hands-on knowledge on specific algorithms, coded in specific languages and applied to specific problems. You can find many such alternative courses. Machine learning has imported much relevant knowledge from statistics and probability theory, but this is not a general course on these fields either. This course will hopefully make you a better computer scientist who are able to handle data analysis problems, but it will not make you a general statistician or data scientist. Even if the focus of this course is machine learning in the context of artificial intelligence, I would like to say a few words about some neighboring areas, like statistics, data science, and big data. First of all, on the slide you see now, you can get a little overview of the situation. On the coming slides, I will say a few words about the different areas. So essentially, 2 decades ago, something happening. Actually, some advances in machine learning get a better spreading, and also a new area emerged, which is often called big data. Actually, based on the rapid growth of data in the world, with, of course, a great need to get these data analyzed. And I would say that these two things together triggered some urge to widen the concept of statistics somewhat with the new umbrella concept that was termed data science. So let's first turn to the area of statistics, the oldest area in this genre, which has a very long history. And statistics has traditionally dealt with a range of activities concerning data, from data collection or data harvesting, data modeling, up to data presentation for decision makers. And in the middle there are data analysis, and of course the big overlap between machine learning statistics is in this middle data analysis part. And of course, in particular, what is very useful and needed in machine learning is input from the traditional area of statistics with respect to mathematical statistics, which is the core of data analysis, which is in turn is based on probability theory. So a lot of input has come this way into machine learning. Also, one can say that there are different kinds of statistics. So the descriptive statistics who only concern with in a good way describing samples, statistical samples taken, without any ambition to draw any wider conclusions from it. From inferential statistics, where the ambition is to really draw wider conclusions on whole population, real populations. And of course, machine learning is much more dependent on what we call inferential statistics. So if we turn now to data science, this area doesn't present much new. It was launched as an umbrella concept for statistics, actually augmented with some other data analysis techniques, developing in the big data field and with advances from machine learning. And as for statistics, data science cover also the range of activities from harvesting up to visualization and precision, and with the same old overlap in the data analysis stage. Actually, the concept was coined around 1996, 98, which is like 20 years ago. But then it was really boosted in this last decade. And it got a lot of publicity in various places. An example of that is this very special article from the Harvard Business Review called "The Data Scientist, the Sexiest Job of the 21st Century," which contributed a lot to this new area's fame. And of course, many young people looked for jobs, and also, of course, relevant education in this new area. In contrast to data science, the term big data primarily refers to storage, maintenance, and access to data. Even if the borderline with data science is some rather blurred. Big data area is based on more traditional areas. One is very large databases, others are data warehousing and distributed databases. The area was born in the late 80s, out of the fast data growth due to explosive development of harvested sensor data, as well as user data from the web, and the parallel growth of traditional databases in a variety of sectors. When we speak about big data, we talk about terabytes, at least, and then up to the 12. And already we talk about zettabytes, then up to 21. But the size is not the only relevant parameter. The variety of data types, the quality, the velocity of generation are also important factors to increase the complexity. This was an excursion in some neighboring areas. So now we turn back to machine learning and an overview of this course. And as you have understood, we have 8 weeks, and the first 3 weeks have an introductory character. So the second week will be a more abstract description of characterization of learning problems, and the third week will focus on different kinds of representations. The motivation for having this kind of part of the course is that all kind of learning have to take place within some kind of representation, and therefore it's crucial to have some knowledge about those kinds of representations that are most common in artificial intelligence. If you already have a good view, good knowledge on that, of course you can go very fast on that part of the course. The 3 middle weeks of the course, 4 to 6, are kind of the core parts of the course. So 2 weeks focus on learning in symbolic representations. The first on inductive learning, in situations where you have no theory or rather weak theory that backs up the learning process. While in the second week we will look at situations where you really have a pretty strong theory of the domain you're working in, and in a sense learn on the border of what is already known. Week 6 is then as a contrast learning in a sub-symbolic representation, in particular artificial neural network. And of course also here there is a distinction between situations where you have some prior theory or not, but it doesn't seem relevant to divide that up in the same fashion as for week 4 and 5. So finally, week 7 and 8 goes into directions. Actually, week 7 looks into the context of cognitive science. Even if in theory, machine learning algorithm could just be pure computer science algorithm. Normally, the way one design this kind of techniques is based upon some intuitions and some knowledge and some inspiration from the way natural systems works, in contrast to artificial. So this week we'll look into some models of learning from various cognitive sciences that has very much inspired the way we do machine learning. Finally, week 7 gives an overview of the current very vast set of tools and resources that are available at this point for doing work in machine learning. It's not an easy area because of the current very strong industrial interest which promotes the development of tools and resources very much. So therefore the hope is to bring some order and some overview of what happens in this area. This slide is aimed at giving you a clearer figure of the order of how one should follow this course. I mean, of course, the bottom line is always possible and meaningful and maybe advisable to go week by week, from week 1 to week 8. But as you understand, there is not always strong preconditions everywhere. So I just want to say a few things here. I say that week 1, week 2, and week 3 are strongly advisable to follow in the beginning, because they give an introduction to the area and the abstractions and the general knowledge that is supposed to be a background for the rest. Then for week 4, 5, and 6, they could be taken in different orders, but still, as this course is set up, it's more favorable to even follow week 4, 5, and 6 in the given order. Because many things that turn up in week 6 in the symbolic representations are in a way mirror somehow what really happens in the symbolic case in week 4 and 5, and as it's now set up is treated maybe more in detail and more thoroughly during these weeks. What is more independent is of course week 7 and 8, because they are extensions of the course in a more theoretical and more background direction, or in a more practical direction. So of course you could probably feel free to look into those whenever you like during your work with the course. So now I'm going to turn to the individual weeks of the course. So my intention is to shortly comment the content each of the week to give you a flavor and a feeling for what you can anticipate to come during the course. I will not go into depth. I will make just a few observations and comments for each part. So this week we will focus mostly in the coming 2 lectures on artificial intelligence. We'll talk both about the roots of the area 60 years ago and what's happened then, and how the profile of the area looked at that point. And then I will make a more general overview of the areas as such and place machine learning within the whole area. Finally, there will be a lecture about applications of machine learning. Theoretically, that lecture could be placed anywhere within the course, but I've chosen to put it here very early because whatever technique we were going to talk about, it will always refer to some applications. So therefore, it's good to have some reference point of this kind early in the course. Finally, I want to comment on the general structure of each week. So every week we'll have an introductory lecture, and which sometimes could be a little shorter, sometimes a little longer. And then there will always be a last lecture, which we call tutorial. And tutorial here means preparations and introduction of the assignments for that week. So in the second week of the course, the goal is to characterize the various situations, various situations which machine learning tries to tackle. And I'm going to say very general that a majority of machine learning techniques want to tackle situations where you have a lot of set of examples, and you study those examples, and from those examples, you want to be able to classify new examples or build up some abstractions. So one of the lectures is try to sort out what is an example, what is an abstraction, how can you characterize an example, and so on. Then, of course, there are different modes of working here. So one way of working is what we call supervised, where all examples are pre-classified. So, for example, we say, let's feed the system with a number of images of a cat. And all the examples are cats. And the only thing that the system do is to build up an abstraction of a cat. The contrast to that is unsupervised, which means that we feed the system with any image of, let's say, any animal or any category, and then it's up to the system to sort out was this a cat, was it a dog, what is something else, which is a more difficult task. Also, one can play with the way you use the examples. So if you want to supervise better or more, you can say these are positive examples, these are negative examples, these are extreme examples, these are typical examples, which also facilitate or simplify the learning process. Another distinction that is important is whether you have all examples there existing in the beginning, or whether all the examples come one at a time in a continuous fashion. The later is also more difficult to handle. Another aspect is whether you learn, let's say, in the blue, so the only thing that exists is your examples, and you build a small theory of abstractions from that. The other extreme is you already have a strong theory, a really strong knowledge base, which you can already use for problem solving. And then what to then want to do is to improve that knowledge base, which means that you learn on the border of prior knowledge. One example of that is what's called reinforcement learning, which is a special case, for example, used a lot, for example, for training robots. It's an example where you want to learn a robot to move the arm in an optimal way. I, of course, have to start with some basic movement schemes. So there is a theory for moving, but you can improve the movement by adapting a number of parameters. But of course, this means that you have to give the system feedback all the time on good movement, bad movement, and so on. And this is a specific kind, I would say, of strong theory learning. Finally, the most ambitious thing here is to learn representation. And by that, it means that normally in machine learning, you have a fixed representation. You have a fixed model of the domain you're working with, and you always learn within that model. However, more and more people understand that it's not very realistic because systems have to be robust and you cannot think about everything from the start. So therefore, there is also a need for the system to learn the representation themselves, learn which kind of objects we should consider, which kind of features we should consider, and so on, which is then another step ahead in the advancement of the field. So the third week will be about various representations used for machine learning. And one can say there are two parts here. First, we can look at the typical symbolic representation that's traditionally been used as the basis for building learning algorithms. And two such are decision trees and Bayesian networks. Also, one can add, and that will also be referred to this week, you can work simply with arrays of different dimensionality, which is a third symbolic way of handling this. The other group are subsymbolic, and that's the typical type of representation in artificial neural networks, and that we will spend some time on. We also mention another kind of symbolic representation, genetic algorithms. We will not spend so much time on that on the course at all, but we will mention it now and then because it complements the picture. finally, I want to comment on a slight complication we have here, because of course in artificial intelligence we want to use machine learning to improve our programs, our problem-solving programs. And actually most systems built historically in artificial intelligence are based on multi-paradigm programming, a kind of combination of logic programming, functional programming, and object-oriented programming. And of course, logically, it would be so that when we learn, we want to modify those programs. But slightly contradictory here, most work in machine learning have been focused on the earlier forms of representation, not so much about learning functional logic and object-oriented program as such. But of course, it's important to know about this contradiction, and it's also important to know the properties of these representations, because in the end, results from learning processes had to be fed into the existing systems. Now we turn to the core part of the course, 3 weeks, where we will look at different kinds of algorithms that has been important in the development of machine learning. And in the first week, week 4, we will look at inductive learning algorithms that work on symbolic representations, but also primarily in cases where we have weak theories, in the sense that we are almost none or very little prior knowledge that guides the learning process. So the first case here is supervised learning. This is the classical case where we learn from pre-classified examples and build up a well-defined set of defined abstractions. The opposite case is unsupervised learning, where we have non-classified examples and the algorithms themselves have to sort and categorize these examples and build the appropriate abstractions. The intermediate case here we will look at is called instance-based learning. In the two first cases, the algorithms build concrete explicit abstractions out from the examples and store these abstractions. While in the last case, we have a system philosophy where we store all examples and do not build any abstractions. That means, of course, we have to have a structure of examples, and when new examples come in, we have to relate them to the old and place them in the structure. So in week 5, we will still look at learning in symbolic representation, but look at a few cases where we combine the inductive learning with the existence of strong theories. And the first case I want to mention is inductive logic programming. I earlier mentioned, when we talked about representation, that it was a kind of contradiction that many machine learning algorithms worked in representations that were not the most important and common ones for really building systems in artificial intelligence. Logic programming is one of the very strong paradigms that has been used to build many systems in artificial intelligence. And 20 years ago, the idea came up that why not re-engineer our inductive algorithms so that they can directly learn logic programming elements. And the first step is, of course, only to mimic what one did earlier in the other form of representation. But of course, the next step is that because we now do everything in the same formalism, we can more easily combine prior knowledge or prior theories expressed in logic programming with the new kind of abstractions that we build up from the inductions of examples. So this is essentially the key idea of logic programming. Another aspect is, of course, that for learning in cases with no prior theory, we need often many examples, because many examples may be bad, may have noise, may be typical or non-typical, and so on. So this means that in order to play out this noise and difference among examples, we need many examples. However, we could also manage to learn from fewer examples, but then in a way we have to make a sanity check of the examples and screen the examples in the in the light of the prior knowledge. So this means that if in appropriate existing strong theory, we can validate the soundness of our examples in the light of that theory, and thereby we could still utilize induction from these new examples, even if there are few. There are a few other things that will be talked about in this week. We will talk a little about learning by analogy, which essentially we have two domains, and we have a knowledge base or a theory in one domain, and we have a much weaker theory in another domain. But we can assume that there are similarities between the domains, so therefore we can infer abstraction in the second domain from the already existing one in the first. Finally, there is also a need in many kinds of systems to explicitly and conveniently directly add new abstractions, not having to reprogram the whole system. But in this case, no induction takes place. It's just that new knowledge pieces are easily added to the system. That was referred to by the term being told. And finally, we have reinforcement learning, where we essentially also have a prior theory, for example, a prior theory for guiding the moment of a robot, but then we want to optimize the functionality of that example, in that example, a robot, by incremental learning. So week 6 of this course covers machine learning algorithms in artificial neural networks. And there is a history of this, and one can say that the structure of lectures is based upon this history. So we start by talking about something called perceptron, which was a very, very early attempt of an artificial neural network. People were very, very positive already in the 1960s about the successes one could have using this technique. However, there was a backlash. People showed that the original designs wasn't really possible to go forward with, and one can say it was a big, long period where not much happened. But in 1986, like 20 years later, this area revived again, and there were some key results in the early 1980s which showed that networks with many layers, actually the perceptron has just typically a single layer initially, but if we build networks with many layers, then and special kinds of propagating values forward and backwards in these networks, one could show successful results. So this happened in the 1980s, and we will talk about what happened in that period. The next step in this process is that in order to really come forward and solve real problem with this technique, you cannot have general networks. You have to, in a way, adapt the networks so they fit certain kinds of issues and certain kinds of problems. And image recognition has been one of the key application areas, and there are special techniques that we will cover. An example is convolution networks, which have specific properties that makes them suitable for handling problems in image recognition settings. Also, the initial networks was not ideal for modeling temporal phenomena, like sequences of events. And in order to handle that, another kind of network type appeared called recurrent networks. And these two kinds of networks had a large importance on the further development, and we will also go further looking at more of these kinds of recurrent networks. Examples of that are Hopfield networks and Boltzmann machines. So since the 90s, there have been a continuous development of this, but I would say the next very strong revival of this area was in the early 2000s, where this area blossomed, and essentially the term used today for the state of the art of this technology is essentially deep learning. I mean, deep learning was coined a long time ago, and the reason for the name is that the successful neural networks need to have many layers. They have to be deep in a sense. But today, of course, this term covers a lot more because it encompasses many of the recent advances on the algorithmic side. And I would say also one very important characteristics of what you can do today in deep learning is to take the kind of last step in the learning problem, which is to learn representations. That is not only learn within a fixed model, but really incrementally modify and develop the model itself. Week 7 of the course, one can say, is a separate part of this course. The reason why it's there is to really show to you that machine learning advances have not happened in isolation as just part of computer science. Many times the designs have been inspired by insights fetched from other areas, which are one can characterize as cognitive science. And parts of cognitive science are, of course, cognitive psychology, neuroscience, anthropology, linguistics, and so on. And during this week, we will primarily look at three things. We will look at some models in cognitive psychology. We'd have to do how we learn categories as humans, how we conceptualize the world, but also models in cognitive psychology that describes how we, as humans, solve problems and how we develop expertise. So that's one thing. Another thing we will look at is some model from neuroscience, which is actually models. Primarily, we will look into how our human perception works. And the third thing we will look at during this week is looking at theory of evolution, because in a large scale, evolution is a learning process, one can say, on an abstract level. So these things we will look into week 7. So finally, for week number 8, we will talk about tools and resources useful for doing machine learning work. When an area is new, there are not much special tools and support systems available. But when an area comes into the limelight, as machine learning has come today, suddenly there is a great interest for all kinds of tool and language provider to see to that area is supported by their tool or language. So today there is explosion of initiatives of various kind to support work in machine learning, and of course this also has influenced the success of the area lately. So the goal of this week is to really try to sort out for you what kind of tools are there, of what kind, and so on, because it is a kind of jungle today, and so not so easy to understand what is what. So in this week, we will look at 4 categories of things. So the first category is named General Technical Computing Tools, and these are general toolboxes, existed for a long time. A typical example of such a toolbox is Mathematica, and which traditionally supported a lot of things, but it didn't support machine learning. But today it does. So this is an example of a kind of tool. But there are, of course, others in the same category, and we will go into that. The next category is termed here general support, software support, which means all kinds of languages, support systems, libraries, and so on that can help you to work in this area. And just to take a very simple example. So, for example, a language like Python is very popular today. First of all, because it's a very commonly used language, very popular language to use for programming, but also that when I made some effort to easily integrate function in that language that facilitate work in machine learning. The third category is more dedicated platform that's been developed specifically for this purpose, for the purpose of supporting machine learning. And there are a lot of companies who develop those. One well-known example there is, for example, Google, that has developed a platform called TensorFlow that is used in many cases. But there is really a large set of similar platforms. Finally, something which is, of course, very important is that there are easily accessible and openly available data sets which you can test your systems and algorithms on. And there's also now starting to emerge a large set of such data sets. A well-known such data set is ImageNet, which supplies a large number of images for all kinds of common nouns. So before we end this introductory video, I want to say a few things about literature. So first of all, I want to say that this course has no dedicated course literature, not one single book that we follow. There are so many books in machine learning, and as you have understood, hopefully now, the area is pretty old. So there are very old books, there are very new books, and there are books that are like in between. I would not recommend you at this point to read the very old books, those from 1980s and so. I would recommend the new ones because some of them are very good. Some of them are always bestsellers, at least within the context of an academic area like this. But of course, the new ones you probably have to buy because you may be difficult even to borrow them, and it's absolutely not possible to access them on the web. But for the books in between, and then I've given you an example here, the book Machine Learning by Tom Mitchell. It was originally published in 1997, but there are also later editions, of course. But for this kind of book, older editions may be accessible on the web because they are not bestsellers anymore. So there are no interest to the publishers. So for me, maybe like a default book that could be useful. You want to read more about the area is this book, Machine Learning by Tom Mitchell. Newer books, I also given you 2 examples here. There is a book from 2014, which is a general introduction by Ethem Alpini. but there are also a book very much talked about, this deep learning book by Joshua Bengio and associates. For this course, on every week, you will get a number of literature references, but these literature references will typically not be books, and they will typically not be survey articles either. So maybe a special feature of this course is when I give you literature references in the various weeks, I will mostly give you reference to original articles or articles that represent kind of breakthroughs in this area at various periods and various points in time. So this is the end of the introduction. Thanks for your attention. The topic of the next lecture will be the foundation of artificial intelligence and machine learning.